there's much more reasons to make difficult the detection of this kind of systems. So first, some of you maybe know that for a few years I'm involved in a project, namely a Troy project, dedicated to the detection of co-orbital exoplanetary. So here you have a list of the main contributors of this project, and the result is this one. So far, nothing has been detected, but time will come, I think. So it's a question of years. Okay, so there's a lot of different reasons for to make difficult the detection of this kind of systems. So of course, the problem of detection due to classical method, the radial velocity, transits, and so on, are not very suitable to detect this kind of system. So I will be very brief, as I'm not an expert of observation. But okay, so two other questions. The question of stability for close-in co-orbital planets, obviously due to dissipative effect like tidal dissipation. And another question that is really a pretext to talk about stability and celestial mechanics is the question of mutual inclination between the two planets. So, but before, what are orbital systems? Of course, the famous first example is the one described by Lagrange, that correspond to the Lagrange configuration, where the three bodies are occupied to vertices of an equilateral triangle here, and then you have a well-known relation of stability. Here are the masses of the planets, and then you have also solutions with eccentric orbits, and then the triangle is always equilateral, but the distances vary periodically. And then you also have criteria of stability that depends on the eccentricities. Okay, so this kind of systems, co-orbital system, are well known in the solar system. For example, you have the Trojan of Jupiter. So the small body, these asteroids, are the same mean motion, average mean motion of the same as the one of Jupiter, and around these equilibrium points, these bodies librate with a long period or slow frequencies around this point. It's called the libration. And it's not only planar, you can add some Trojan time, maybe the maximum is about 40 degrees in the solar system. You have also these well-known satellites of Saturn. So you have Thetis, which possess two co-orbitals with so Calypso and Telesto, with very small amplitude of libration around the equilateral configuration. Also Dione, with a moderate amplitude of libration, to larger here, it's about 30 degrees. And then you have the famous example of Janus and Epimetheus. It's very close to Saturn, close to the outer rings. And then in rotating frame, these bodies are on horseshoe orbit. So it's called the horseshoe orbit. And here it's the tail orbit. Okay. So you have other examples in the solar system. Exoplanets co-orbital systems or resonance. So there's many authors that wrote on the question of the existence of or formation of co-orbital exoplanets. Here you have a list, a non-exhaustive list of authors that work on this problem. And then the probability of generate co-orbital system at the end of the formation depends on the kind of the mechanism of formation. You have two kinds of mechanism: the in situ formation and then the migration and capture in resonances. And then, depending on the author, on the method, on the parameters of the disk, for example, the probability to have this kind of system ranges from something that is very small to about 20 to 30%. So it depends, it strongly depends on the gas disk and on this component. So it seems that this system exists, but we don't have a fine co-orbital system. So why? So one of the reasons is this one. So I will be very brief, but it's due to the classical method to detect this kind of systems. So, for example, the first one is the radial velocity. So you monitor the radial velocity of the star. But if I know something in okay. But if you have co-orbital planets which are close to the equilateral equilibrium, so you have as it's a one-to-one resonance. The two planets have the same mean motion, so we'll see only periodic motion. The curve is periodic, and then you get the same signal that the one generated by only one planet of mass this quantity. It's larger than the mass of the sum of the two planets. Okay. You have amplitude of libration. Here, the radial velocity signal, this one, so the short oscillation are the short period, the orbital period, and then you can have modulation of this signal, and the amplitude of the modulation depends on the amplitude of libration of the pulse. Okay, but the most favorable case, okay, is this one, when the two planets, the two co-orbital, have the same mass, the same masses, and you must have very large amplitude of libration, and then you need to have a lot of observation data. So otherwise you cannot see the modulation. So it's very rarely the case. So the second method is of course the transit method. So when the planet crosses the disk of the star, you have dips in the light curve, and if the two co-orbital transit, okay, you will have this signal, and if this signal is periodic, okay, you are sure that you have a co-orbital planet. But in fact, it's not so sure. You have this example of the system of counter example of TOI 178. So the short story is that TESS spatial mission observed several transits. I think it was the 6 transits. So on the pipeline, it's automatic. The pipeline attributes these transits to two planets. So the transits of two planets and the planet with very close orbital period. These two periods. So the only solution to a stable configuration is that these two planets are co-orbital, so in the one-to-one motion resonance, and with a quite large amplitude of libration, maybe in a horseshoe situation. Okay, so that's the point. But in fact, this system was so interesting that the science team of CARES, this spatial mission, dedicated 11 consecutive days of observation to study the system. And then, what CARES found is that no orbital planets, unfortunately, but fortunately, a very nice system with 6 planets, and more of the 5 of these planets are in a resonance chain. So why this confusion between the co-orbital and something else? Yeah. So one point is that the planet with 9.96 days of period were definitely there. Okay. But what about this one? So this one test observed 3 transits of this planet. But in fact, it was the combination of transits of 2 planets in close to 4 to 3 mean-motion resonance. We can imagine that. No. Here, at the beginning, the first transit was the transit of the outer planet. Okay. So when the outer planet transits, the inner one was in a quadrature. So 10.35 days after the inner planet transits, so it's the second one, and then 10.3 days after the outer planet transits again. So you have 3 transits separated by this. And then, as the 2 planets, unfortunately, have more or less the same radius, so the depth of the transit was the same, so it's impossible to make the difference between these planets. So it's not so easy. You have another problem, the one of the mutual inclination between the planets. So you can have, no, maybe the first case is the case of the radius of one of the co-orbitals is too small to be detected by transit method. So, okay, and then the second one is that when you have mutual inclination between the 2 planets, and a few degrees is enough to for the second planet, the inclined planet, not to transit. So in this case, but I will be very brief. You have different methods to try to detect the system. Of course, if you have transit and TTV, so the periodic variation of the transit, you can try to do something, but it's extremely difficult to make the difference between co-orbital resonance and the other mean-motion resonance. It's quite impossible. And then you get the same signal than if you have a distant moon, so you cannot make the difference. And then you can try to do something else also, is to combine radial velocity of transit. In this case, you can have a time lag between the time of the transit on the time where the radial velocity is minimum, but it appears also in the case of a single planet in eccentric orbit. So we have to constrain the eccentricity of the planet. So it's quite impossible. You have to to observe the secondary transit of the planet. In this case, you can so the eclipse. So you can, in this case, deduce the eccentricity, but it's extremely okay. So the second point, the question of stability due to tidal dissipation. So in 10 years ago, Rodriguez, Dupont, and Mitchenko make two numerical simulation. So they take, in this example, a star of the same mass of the sun on two Saturn masses with dissipation, and then they in co-orbital position, and then they integrate this numerically this system with tidal dissipation, and then they observe that here it's the amplitude of liberation, the angle, the angular distance between the two planets, and it increases, and after some period of time, the system leaves the resonance after a close encounter. Okay, so and they do the same simulation with two planets of two super-Earths, and they get more or less the same result. So this raised a few questions. So, do time destroy co-orbital systems? So is it the case for all masses? You have only two examples, and for all kind of tidal dissipation. And then the important question is the time scale of this phenomenon, and then what is the indication for co-orbital planets. So before trying to answer this question, I will briefly describe the conservative dynamics for co-orbital planet, and then so oh, nice. I think there's something wrong, but okay. So I will try to do something without that. Okay, so first you can, I think that in the first slide, as you can see, it's the perturbative function, and it's the problem. So you have, as usual, you have two planets on a star. The mass of the two planets are small with respect to the one of the star. You have a small parameter, for example, epsilon, which is the border planet divided by the mass of the central star, and then you can write this Hamiltonian using, for example, radiocentric canonic coordinates. Okay, then after you will try to introduce elliptic elements, or not elliptic elements are not canonical, but Poincaré coordinates are, so you use Poincaré coordinate. So I would like to introduce two variables, x, which is more or less the eccentricity of one of the planets times what's the name of this? The position of the longitude of the peridium, plus something of order 3 in eccentricity. And then you have the same kind, y, for the inclination, which is about the inclination of a planet exponential by the longitude of the ascending nodes, plus something smaller. Okay. And lambda is the conjugate of small lambda, which is the longitude of the mean longitude of the planet. And then you have angular momentum, which is an integral of the motion. Okay. Now, yes, what is important is that, so it's here. So, okay, you are in the one-to-one mean motion resonance, the co-orbital resonance. So the two average mean motion are equal to some quantity that I the n bar. Okay. So in this case, as it's the case in mean motion resonance, you have three different time scales. So you have fast angles, variables, so the mean longitude, the position of the planet on the orbit, for example, it's of order 1. You have the resonant angle, the difference of the mean longitude, which is a semi-fast angle because its frequency is of order the square root of epsilon, and you have also secular frequencies that are related to the motion of the ellipses of order epsilon. So I don't know if it will work. No, anyway. So you can, as you have, you can average this the Hamiltonian on one of the fast angles. So okay, you average the Hamiltonian, and then you have something that depends only on zeta, the difference of the two longitude and the secular angle, and the corresponding conjugated variable, which is, I don't know if it will appear somewhere, but it is a variable that corresponds more or less to the difference of the square root of the two in motion multiplied by the planetary masses. Okay. Oh, it's the same thing. Okay, anyway. Ah, yeah. I don't know if I can. No. Yes. Okay. Thank you. So yeah, it's the same thing. So the variable y on x and so on, you have a first integral related to the angular momentum, which is the total, which is constant, and then yes, okay. So you can have, it's the conjugated of this one, and then you average Hamiltonian, and you the new Hamiltonian. Here you have the Keplerian parts that depends only on Z, and we have time. And the average perturbation. Okay. So now, if you want, you can expand the Hamiltonian in terms of x and y, so in terms of eccentricity on the inclination. So when you have Kepler, and then when you expand the perturbation, you have a series of this form with coefficient that depend on the resonant angle. And then the important thing is that the total degrees in x, so in eccentricity, is 11, and then it's the same for the inclination. So you can deduce that if you make x equal to 0 in the Hamiltonian or in the corresponding Hamiltonian system, if you start from circular orbit, you also remain in the circular case. eventually you can have inclination. And on the other side, of course, if you start with a planar orbit, you conserve the planar orbits. And on the intersection of these two manifolds, of course, you have the circular planar orbits. So let us first study this dynamics. Okay, so with some approximation, you can consider that the Hamiltonian corresponding to the circular and planar co-orbital dynamics is this Hamiltonian. So it's a function here that depends on theta, and the Hamiltonian, of course, is a 1 degree of freedom Hamiltonian. So it's integrable. And here you have the phase portrait of this system, of this Hamiltonian system. Here is the difference of the mean longitude. And here, Z, that corresponds to more or less to the difference of the two mean motions. So when Z equals 0, not the mean motion, the semi-major axis. So when Z equals 0, the two semi-major axes are equal. So, of course, you have 3 fixed points. So this one corresponds to the Lagrange equilateral solution configuration. Of course, here in this with this Hamiltonian, it's stable. This one corresponds to the Euler unstable Euler configuration when the 3 bodies are on the same line. On the other one, it's the symmetry of Lagrange that correspond to L5 in the restricted 3-body problem. Okay. And now the blue trajectories correspond to small here, or not too small when you approach the separatrix, deformation of this equilateral triangle. So it's periodic deformation. That's called the dipole orbits here. And then outside the separatrix, you have the very large amplitude of libration that correspond to horseshoe motion. So just here, these two fixed points are stable, and this one, of course, is unstable. But it corresponds only to the circular planar motion. So it's what you have. But you can study what happens in the transversal directions. So, of course, in the transversal direction, you have X and Y that correspond to what happens when you give some eccentricity to the system or some inclination. Okay, so to study this kind of stability, transversal stability, you can linearize the system around one of these periodic orbits, and then write the variational equation and study this equation and so on. So here I will just study the very simplest case when you are at the fixed point of the circular planar problem, so the Lagrange configuration. But you can do whatever you want with this kind of system. So okay. So you start with the fixing point of the problem, so the Lagrange equilibrium, and then you expand. So it's not difficult to expand around this quantity because the eccentricities here are the equilibrium correspond to the eccentricity and to the inclination equal to 0. So you only retain the quadratic part in X and in Y. Of course, I don't know if it's obvious, but you have a very strong degeneracy in the vertical direction because the quadratic part corresponding to the inclination is equal to 0. Okay, so it's a problem to study the stability in this direction, but we see this after. Okay, so we will study the blue part here. Here it's, so this corresponds to the direction, to the planar and the circular direction, and here correspond, blue here to the eccentricity. So now, as I said previously, the frequency here corresponds to the semi-fast frequency of order square root of epsilon. So if you study this system, the blue system, you have symmetries, and then you can write the system as something like that, where the matrix depends on the masses of the planets in first approximation. And then it's easy to compute the eigen values and the eigen frequencies. And what is this one? So you have, of course, two eigen frequencies. The first one is given by this quantity. The eigenvalue is equal to 0, and the eigenvector is this one. And you can realize very easily that it corresponds to that. So it's the Lagrange equilibre, but eccentric Lagrange equilibre. So you have one eigendirection that corresponds to eccentric Lagrange configuration. And what happened in the other direction? So the other eigenvector corresponds to this vector on the frequency, the eigenvalue is purely imaginary and different from 0. It's of order epsilon, so it's something secular. And then it corresponds to something that has been called by Dupont anti-Lagrange configuration. Why anti-Lagrange? Lagrange, because if you start from here, the Lagrange equilibrium, and if you take the new orbit, and if you rotate this orbit by pi, you get ratio. One main difference is that in Lagrange, the two eccentricities are equal, of course, and in the anti-Lagrange configuration, this equality is ponderated by the planetary masses. So this is not the eigenvalue is not equal to 0. So you have to your two ellipses here that are locked, but rotate with this precession frequency of order epsilon. So you have a family of periodic orbits along the P1 direction, and along P2, it's a family of periodic of fixed points. Okay, so you can presume this situation like that. You start from Lagrange circular. So when eccentricity equal to 0, you linearize and you compute the spectrum. So the spectrum, you have the I nu and minus I nu that correspond to what happened in the circular planar motion. You have two 0 eigenvalues that bifurcate when you have eccentricity in Lagrange eccentric configuration, and then the other one that are not equal to 0, the secular frequencies that corresponds to the anti-Lagrange configuration. Okay, now what about stability when you have tidal dissipation? So I showed you this plot previously. So we have this question, and to answer this question, it's not very difficult. You can select a brilliant student, you ask him these questions, and a few years later, he comes with the solution. So what are the solutions? So this is the PhD thesis of Jérémy Couturier. And the answer are, yes, it's always the case. So tides always make a co-orbital system unstable. And it's the case, it's independent of the masses or the tidal dissipation coefficients. But what is very important is that the time scale of destruction of this system depends strongly on the parameters, the planetary masses, the dissipation, and so on. And then Jérémy Couturier developed analytical expression of this time scale. And then the last question, yes, it's a problem for co-orbital exoplanet. Probably you cannot have stable, or you cannot have closed-in co-orbital systems. So to study this tidal effect, so you start with the average Hamiltonian, the one I showed you before. You derive the associative average Hamiltonian. Then you add contribution of the tidal dissipation. Of course, it's no more an Hamiltonian system, it's dissipative. And then you find a fixed point, you compute the eigenvalues, and then you can reduce the time scale of characteristic time scale. And then you also can integrate the average system numerically, and it's much more faster than the not average system. Okay, so very briefly, the tidal dissipation. Here we use a very simple model. We assume that the Q, the dissipative factor is constant. So as delta T, the time lag between the position of the perturbation, the perturbing body, and the rays of the tidal bulk. And then we also simplify the model, assuming that we have also dissipation on the planet or not on the star. But it's by far the main contribution. So, yes. So that's the spectrum I've shown you just before. If you start, so with that tag, you start with the Lagrange circular problem. You have these eigenvalues, okay, and then also you have rotation. You have the two planets that rotate. But as the planets we choose homogeneous pair, of course, you have no coupling between the rotation and the orbit. So you have 0 and 0 eigenvalues to this system. Now, if you have, I don't know, if you had tidal dissipation, you have also a fixed point which is very close to the previous one, the Lagrange circular. Slight deformation of this, but now you have coupling between the rotation on the orbit. So the rotation, the equilibrium is close to synchronization, but not synchronization, close. And then the eigenvalue in black, it's the eigenvalues of the conservative problem, of course. And then when you have dissipation, you have two parts. The blue part that is not really important. It adds some it modified the frequency of the precession frequency and the libration frequency very slightly. And here, the second eigenvalue, which was equal to 0, is no more 0. It's something very small, but different from 0. But the most important point is this one. You have now, before the fixed point was degenerated but stable, elliptic, on here, now you have real parts that are different from 0. So, yeah. So now I concentrate only on this real part of the eigenvalue. So the first one corresponds to the rotation, and then as it is negative here, you have the fast synchronization, not exactly synchronization, but it tends for an equilibrium of rotation. Why fast? Because here you have here it's the radius of the planet, so you have this quantity to the power 3, and here, hidden here, that's the same quantity, but to the 5. So of course, it's in absolute value, here it's large greater than this quantity. So first you have synchronization, more or less synchronization, and then here, these two eigenvalues correspond to the eccentricity, of course, are associated to the secular motion. And as you can see, you have a negative, these quantities are always negative. So you have circularization, the eccentricities down to 0. Okay. Here you have a numerical simulation, but you see that it's the case.
Sorry.
Yeah.
But these terms are really proportional to the inverse of the mass ratio.
Yes. But the mass ratio, the masses of the planet are hidden here, because here you have the radius of the planet, and you can assume that when the mass tends to 0, the radius, okay. So it's not. It seems to be, but it's absolutely not. If you link, of course, obviously, the radius to the mass. By doing so, you have a limit, which is not 0. And the most important point is this one. Here, the frequency, it's not the frequency, the eigenvalue associated with the libration here is positive. It's real part. So you have divergence, and it's what you can see here on this plot. So you have several simulations of the same problem, but with different masses and dissipation coefficient. But in all these cases, you see that the amplitude of the libration increases exponentially. And what is very interesting is that the coefficient of this exponential function is exactly this one. It can be quite surprising, because here is what you get in a neighborhood of the fixed point. But here you see that in the whole, what's the name, spectral region, you have the same exponential divergence. So you start close to the fixed point, then you spiral outward, and then at what point you cross the separatrix, something here, for example, and here you reach another regime of dissipation when you are in horseshoe orbits. Okay, but so here it's for the average problem, and then to compare, we have integrated numerically the full problem with dissipation and so on, and you see that you get the same result, except that you have something that is different here. But here what happens in the numerical simulation is that you have close encounter with the planets, and then you leave the co-orbital resonance. But so in the simplified system secular here, the whole space corresponds to the resonance. So you cannot leave the resonance in this with this approximation here. Okay, but what you can see is that the time that you stay in the resonance in the horseshoe regime is very small with respect to the one in the temporal regime. So you can consider that when you cross the separatrix, more or less, the system will leave the resonance. Okay, so this gives you the time scale, and the inverse of this quantity gives you the time scale of the time life of the system, the co-orbital system. Of course, you see that it depends strongly on the masses, Q, which is the dissipation factor. So it depends on all these quantities. Of course, the radius of the planet and so on. And just to end with this point, here you have a map that gives you this time scale. It's the time of the life of the system inside the co-orbital resonance. So here you have two different systems. You have the blue that corresponds to a star. The mass of the star is here in solar mass. And you add two rocky planets with Earth mass planets. And then here, the difference is that it depends on the, the distance to the star, the initial distance to the star, which here is given in orbital periods. So it's very short. It's in a few days here to less than 8 days here. And then on the curve, you have the time of that during the system stays in the resonance, the co-orbital resonance. So you can see that in the two cases, it's very short, or it's in giga-year, of course, but it's always here when less than 1 or 2 giga-years. So what you can expect here, to compare, you have the orbital period of transiting exoplanet. On here, the red line here corresponds to the 3.5 orbital period. So you have a lot of systems that are detected by transit, that for which we would expect that we cannot have orbital system or stable co-orbital system. Of course, it depends on the parameters, the dissipation parameters of the planets, and we don't know what are these coefficients, but it's just to have an idea. Okay, so now the second point, on the last point, is the question of mutual inclination. In fact, as it's written here, it's just a pretext to talk about stability of mutual inclination and celestial mechanics. So, okay, you can have this situation here. A few degrees are enough to prevent this planet, one of the two planets, to transit. So you have the transit of only one planet, and you have to try to deduce that you have co-orbital. So it's very difficult. And this is not so unlike because some simulation on the of migration on the disk, sometimes it shows that you can mutual inclination can decrease. Someone, it's not the case, but it depends one more time of the parameter that you put on your disk. Okay, so now this map here, it corresponds to numerical simulation of co-orbital system. So yes, in this case, it's the two planets have the same mass, but it does not really much depend on mass. We start with initial equal to major axis, and then the two nodes are in opposition, as it is in the invariant plane, and the initial eccentricities are also equal to 0. Then here it's the initial difference of the mean longitude. Of course, if you have Lagrange configuration here and there, and here it's the initial mutual inclination. So if you start with 0, you are in a circular planar configuration, and then you increase the inclination. And here you have two different regions here. The blue one, where the eccentricity remains very close to 0, and suddenly, when you increase the inclination, you have some kind of separatrix, some kind of something here, and then you have a new regime, and in this regime, the eccentricities increase very rapidly, and then the system can be unstable in quite short band. So why this boundary here? Can we find an explanation for this question? More or less, I think that yes, we have something. So we have this boundary, and this boundary here corresponds about to 62 degrees of mutual inclination. And if you change the planetary masses, you can see that you have quite the same result, maybe 63 or 5 when you reduce the planetary masses, but it's quite always the same thing. And the boundary does not depend on the mass. So you can do the same thing as previously. So now okay. So yeah, I showed you before that you have a problem with the inclination. You have the quadratic part is equal to 0. You have degeneracy. You cannot do anything with that. So you can solve the problem using Jacobi reduction, or it's the reduction of the nodes. So this reduction is very easy if you consider that if you define your elliptic elements with respect to the invariant plane, that's the plane which is perpendicular to the total angular momentum, on which include the planet, the star. Sorry, here you can see easily that the ascending node of one of the planets is equal to the descending node of the other one. Yeah, okay, see that. So the difference of the nodes is always equal to P. So you have the two inclination, but in this reference frame, the mutual inclination is the sum of the two inclination, and then you have a relation between the modulus of the total angular momentum and the eccentricity, of course, and the mutual inclination. Using this relation on this one, you can remove these 2 degrees of freedom. So you are left with 4 degrees of freedom Hamiltonian. You can do it for more than 2 planets, but it's much more difficult. Okay, so briefly, x are not exactly the same. Here it's not it corresponds to the eccentricity, or it's no more the longitude, but the argument of the periodion. So you can also average the system and so on. Then you have something like this. So now the coefficient here depends on the mutual. Rather than the module of the angular momentum, which is a parameter, you can choose the maximum mutual inclination. It's relative. Okay. If you look to the circular orbit here, so it's the inclined circular orbit. So you have the same phase portrait if the mutual inclination is equal to 0. If you increase, you have it's the same topology, but it changes a little bit. The separatrix shrinks here. Then you increase, you have also the same topology, but it's much smaller. And then, for example, for this inclination, you have a bifurcation between these 2 phase portrait. So you can summarize this bifurcation in plotting the location in the difference of longitude of the fixed point that you have here. So here, of course, you have the one that corresponds to L3, but L3 with mutual inclination. Here, you start from L4 and 5, and when you increase the mutual inclination, you have collision of these 3 families. You have bifurcation, the topology of the fixed point changing, and then after it becomes stable. But here, as it's the circular problem, of course, you have collision, it's angular. Okay. So now you have this solution. You have this fixed point here that corresponds to the circular inclined motion, and you can linearize the Hamiltonian around and so on, and compute the eigenvalue. And what you get is that if here you have the mutual inclination, so at the beginning you have eigenvalues, of course, with real part and imaginary part. At the beginning, you have only something which is elliptic. You have a purely imaginary part on 0 for the real part. And then when you reach in this case, 62 degrees. You have also bifurcation in the vertical direction. And then you have real part, which is no more equal to 0. And there you are in this situation where the eigenvalues are not imaginary, purely imaginary, or not real. So it's probably the reason why this inclination, eccentricity increase suddenly when you reach this bifurcation. Yes, so it's the superimposition of the two plots. You saw that it corrects for more or less something which corresponds to maximum of stability. And then you can show here, you can prove also that you have the same phenomena here. So here I've studied just along this fixed point family, but here where you have periodic orbit, you have the same bifurcation. So we can think that this is the reason why it's suddenly unstable above a certain boundary here. And just to conclude, we are trying to observe this co-orbital system, and I'm very optimistic